so y'all go ahead and do the factoring and the math knowledge question for today. Pause the video, and then once everyone is finished, you can unpause the video, and I'll go over the correct answers. So this factoring is going to factor as x squared plus 9, and then x squared plus 5. Since those are sums of squares, they won't factor any further, and so you'll leave it just like that. For the math knowledge question, it asks about finding the height of a cylinder that they give you. They tell you the volume, and we know that the volume of a cylinder is the area of the base, r squared, times the height. They tell you the volume is 1,000, and that the diameter is 10. So that means that your radius is 5. So now we just need to divide by 25 pi, and the divide by 25 pi. Now, when you plug this into your calculator, you need to make sure that you do 25 pi in parentheses. And whenever you divide that out, you're going to get about 12.7, which is closest to D, 13. So moving on to the lesson. We're looking at lesson 74 today. We're dealing with fluid force. So hopefully after this lesson you'll understand fluid force. This is kind of related to a physics concept, but we're going to be using calculus in order to do this concept. So the weight of an object in a gravitational field equals its mass times the local acceleration of gravity, which is 9.8 for calculus. Whenever we're dealing with physics, it's 9.81. But that would be your weight of your object. It's just your mass times your gravity. For water, the weight density is 9,800 newtons. So this block that we are looking at here on the left is for water. And it's fresh water at a temperature of 4 degrees Celsius. So 1 cubic meter of fresh water weighs 9,800 newtons. The weight density of an object is the weight divided by the volume. So the weight density here is 9,800 newtons per cubic meter. And then on the right-hand side, they show you that the weight of the water is evenly distributed over the whole bottom of the cube. So the average weight of the water at the bottom is 9,800 newtons per square meter. If the water was deeper, let's say it was 3 meters deeper, then the weight at the bottom would be 3 times your 9,800 because it's 3 times as much pressure. Moving on to this next picture, the pressure exerted by a fluid at a depth of h below the surface of the fluids is equal in all directions. So all of these objects have the exact same pressure at the bottom. Even though they're different shapes, they are the same fluid and they're the same distance down, and so they're going to have the same pressure at the very bottom. If you think about swimming in a pool, if you start at one end and you swim the same depth underneath the surface of the pool, even as you go into the deep end or as you go into the shallow end, you have the same pressure on you. You only have more pressure as you go further away from the top of the pool surface. So looking at our formula for force, it's the W, which is the weight density, times the height, which is the H, and then times the area. And the H is going to be the depth of the fluid. It's always going to the top of the fluid or to where it's getting moved. We'll look at when the fluid gets moved in a later lesson. But your H is always going to the top of the fluid or where it's getting moved. And then the W again is the weight density. They're going to give it to you except for water. They're going to expect you to know that water is 9,800. But if it's another fluid besides water, they will give you the weight density in the problem. So let's look at an example. We have a rectangular tank 6 meters deep, filled with water to a depth of 5 meters as shown in the cross-sectional view. We want to find the total force exerted by the water on the end of the tank. So we're going to have to set up an interval here. And so we're going to start by figuring out where our fluid is. Well, to do that, we want to set this on the XY coordinate plane. And it makes sense to put that bottom left corner at the origin because it'll make your numbers a little bit easier. You don't just want to throw it on the coordinate plane. You want to put it in a good location. And so our endpoints that we're going to integrate are going to be from 0 to 5 because that's where our fluid is. So from 0 to 5, that is where your fluid can be found. So your fluid is from 0 to 5. Now our formula was W times H times area. So W is our weight density, which is 9,800 because we have water. Now the height here is 5, and then we are looking for the height as it changes because the pressure, the force exerted on the water or by the water is going to change as you get further down. There's going to be more pressure down here. The height is always measured going up to the top of the tank. We're going up that direction, and then this part here is the Y. So as we move up, the height will shrink. Your H plus Y is going to equal 5. And so the height here is going to be 5 minus Y because it depends on if you're right here, or if you're here, or if you're here as to what the depth of the fluid that you're looking at actually is. So our height is 5 minus Y. And now for the area. Well, on this one, the length of our figure stays 8 the whole way because this is just a straight line, a straight vertical line. So our area is going to be the base, which is 8. And then the height of it going up this way is going to depend on what Y value you're at. It's the change in your Y, which we write as dy. So it depends on where you are in between the 0 and 5 as to what your actual height of your rectangle is going to be. So now what we're going to do, I'm going to go ahead and pull out the 9,800 and the 8, multiply those two together. 78,400, and then we're going to integrate 5 minus Y with respect to Y. So if you integrate that, you'll have 5Y minus 1/2 Y squared from 5 to 0. After that, you're going to plug in 5. So we have 5 times 5 minus 1/2 5 squared. And then we have to plug in 0. And you're going to subtract it, and when you plug in 0 on this one, you do get 0. So now we have 78,400, and then 25 minus 25 over 2. 25 minus 25 over 2 is just 25 over 2. So we multiply our 78,400 by 25 over 2, and you get 980,000. And since this is a force, the units on it would be newtons. And so that's going to be your answer there. So we're going to look at another example. I know that these will take a little bit of time for some of y'all to understand. But hopefully as we do some more examples, it'll make a little bit more sense for you. It's the same setup for each one, just a slight variation. Okay, so we are going to have the figure shown 6 meters deep, filled to a depth of 5 meters with some liquid. We want to express the total force on the end of the tank as a definite integral, given that the weight density of the liquid is 4,000 newtons per cubic meter. Now it says set up the definite integral only. It did not say to solve it. So that's a good thing. You only have to set up the integral. You don't actually have to get to the final answer. So we're going to set up our integral. we're going to integrate. Well, where is our fluid? Before we can figure that out, we need to put our x and y axis. So now that you have your x and y axis, where is your fluid? It's from 0 up to 5. So our endpoints are from 0 to 5. Our weight density, they told us, is 4,000. Our height, well, this part here is 5. We go up h, we're going down y. And so h plus y equals 5. So again, our height is 5 minus y. We also need to find our area. Now this one is different because as you go up closer to the surface of your liquid, you see how the length that I'm drawing is getting longer? And so the way that you figure out what the length of your rectangle is to figure out the equation of this line here. So we know that that equation is going to be a straight line. The slope, we go up 6. And if this bottom base is 8 and the top is 10, this part right here is a 2. So we go up 6 and over 2. That's a slope of 3. And then we know that we go through this point 8, 0. So if I plug it into this formula, I can find my y-intercept. My y value is 0, my slope is 3, and then my x value is 8. So I end up with y equals 3x minus 24. However, I need it to be in terms of y, so I need to solve that for x. So if I solve that for x, y plus 24 equals 3x, and divide by 3. So x is going to equal 1/3 y plus 8. So on this one, our length of a rectangle is going to be 1/3 y plus 8. And then the height is still dy because it changes as you get closer to the top of the surface. So again, the reason that we had to use the 1/3 y plus 8 instead of just 8 is that this is getting wider as we get closer to the top. And so the length of it's no longer a rectangle, the length of your figure there it becomes a different number as you get closer to the top. It gets bigger. Okay, so what they do now is to factor out or pull out the 4,000, and then they actually distribute these two here. And so we're going to have 5/3 y plus 40 minus 1/3 y squared, and then minus 8y. And then we can combine the two terms there that are both y's. So we have negative 1/3 y squared. 5/3 minus 8 is going to be negative 19 over 3y. Then we have plus 40 and then dy. And so again, it says to set it up only. So this right here would be your answer. Sometimes the book will tell you just to set it up because it just wanted you to practice setting up the integral. It didn't want you to spend all the time to actually solve the answer. Now, if you are curious what the answer is, the book gives the numerical answer on page 383. So if you want to check and see, you are more than welcome to see if you would integrate it correctly. But all it had asked for was for you to set up the integral, so you don't actually have to solve it. Looking at the next example, we have a cylindrical tank, 20 meters long, whose radius is 4 meters as shown. It's half filled with oil, whose weight density is 3,000 newtons per cubic meter. This one says set up an integral whose evaluation will yield the total force exerted by the oil on one end of the tank. So for this one, we set up the integral, but we do not have to solve it. It says set up an integral that if you evaluated it, would give you the total force exerted by the oil. All right, so what we need to do first is to put it on the X and Y axis. Now it's a circle. The easiest way to do this is going to be to center it at the origin. So I'm going to center it at the origin. The radius is 4, so I'm going to go ahead and mark that these are 4 and -4. And now I'm going to fill in my fluid. It's half filled, so that means that the fluid is going to be here. So we want to set up an integral. We start with our endpoints. Well, the fluid is going from -4 to 0. So that's going to be our endpoints, -4 to 0. Then we're going to have the weight density. The weight density here is 3,000. And now we have to do the height. Now, since this one is below the x-axis, when you go to do your height, it's going to change it just a little bit because it's below the x-axis. Your height always goes to the top of the fluid. So our height is always going up. Now our y is always going from the x-axis into the fluid. So our y is going this direction. They actually end up going opposite directions on this one. So your height actually equals -y. I'm going to go back here. If you look, your y was going from the x-axis into the fluid here. It was going up into the fluid. Same thing on this one. Your y is coming from the x-axis going into the fluid. Okay, so that's why on this one, whoops, your y is always coming from the x-axis and it's going into the fluid. So your height here is going to be -y. Now, for the length of this one, it depends on the equation of the circle. Because do you see the green lines? They get bigger as we get closer to the top of the oil. So the equation of this circle would be x squared plus y squared equals radius squared, which is 16. And so you solve for x. And so you take the square root, and your x will be 16. The square root is 16 minus y squared. Now, this equation is for only our positive x values, which is this side of the circle only. And so we need to figure out for both the third and the fourth quadrant, but this equation here is really only talking about the part that's in the fourth quadrant because that's where our fluid is. So we're going to need to multiply by 2 to be able to use just the square root of 16 minus y squared. We're just going to double it because it's a circle. The part that is in the fourth quadrant and in the third quadrant, those are the same amounts. So when we have this radical of 16 minus y squared, we just need to double it so that we get both sides of our circle. That is the length, and then the height for your little area part is going to be dy. And so then all they do is to make it 6,000. They pull out a negative from right here, and then they have from -4 to 0 of y, and then the square root of that dy. So this would be your answer. So that's how you would set up the integral. And then they tell you what the answer would be. They do show you to integrate it. They show you how to integrate it at the bottom of page 383. Now, if you want to be stubborn and you don't want to put your circle at the center of the, you don't want to put the center of your circle at the origin, which I have had students that do not want to do it that way. If you look on page 384, the book does show you how to set it up so that the circle is above the x-axis, that the bottom of the circle is set at the origin. And so your integral would be set up a little bit differently. And so you'd have to understand how your answer would compare to the books if it had asked you just to set it up. So if you really want to set it up where your circle is not centered at the origin, check out the page 384 work, and that'll go over it for you. But I think that this way is the easiest way to do it, but that's just my opinion. So hopefully that helps you with fluid force. On your homework, you do get to omit number 8, 14, and 15, so make sure to do that tonight so we can go over it tomorrow.